Okay, remember our mass on moving wedge problem? We have already solved it using the Newton approach, and this time we'll be using the Lagrangian approach, right? And we assume, as before, that there are no dissipation forces. So the wedge can move and the little mass m can move, so we have two generalized coordinates, which I've shown here in green, q1 and q2, and there I have a frame that is fixed to the wedge as before. Remember that the observer is on the wedge, so it's non-inertial. So as usual, we'll try to write down what we need. So it's the, let's change colors. So it's the kinetic energy, right? So this thing here has mass m. Well, for the wedge it's kind of easier, yes. So you have something like that. And for the small mass, I'll write it like that for the moment. You need the speed of this little mass squared. So the question is, how are we going to obtain this one, right? So we'll write the position vector of the mass, right, in the coordinate frame xy, and this is simply q2 cos theta minus q2 sine theta, and of course you can use it to compute the velocity in the same frame. Let's just make the derivative, so it's q2 dot cos theta and minus q2 dot sine theta. Okay, so this is in this frame that is indicated in blue, but I have to take into account that, of course, this wedge is moving. Okay, so if you want the velocity vector of the little mass, we have to account for the speed of the wedge. So we obtain something like this: q1 dot plus simply what we had before, q2 dot cos theta, and minus q2 dot sine theta. Okay, so now we can take the magnitude of this one, and this will give me Vm. Well, I'm going to compute Vm squared. This is dot. Oh no, there is no need for a dot over here. It's already a speed, so I don't need a dot, and I don't need a dot either. Okay, so let's continue. How can we compute the magnitude squared? Well, it's q1 dot plus q2 dot cos theta squared plus q2 dot sine theta squared. Well, the square, I'll put the square here also. It's the whole thing that has to be squared. So let's do the math. It's q1 dot squared plus q2 dot squared cos theta squared plus 2 times q1 dot q2 dot cos theta plus q2 dot squared sine squared theta. So this will give you q2 dot squared. So we obtain q1 squared plus q dot here dot squared plus 2q1 dot q2 dot cos theta. Right? So my kinetic energy is a half. I can write it like that, right? I have this mass and this mass, q1 dot squared, yeah, so plus the little mass q1 dot squared plus a half the little mass q2 dot squared plus m q1 dot q2 dot cos theta. So that's the kinetic energy, and luckily the potential energy, it's much easier. It's mgy. Why we have it over here. Okay, we have been doing this before. It's minus mg q2 sine theta. So now we have everything that we need to, well, compute the equations of motion using the Lagrangian formulation. Okay, so I have rewritten here my kinetic energy and my potential energy. I can then write the Lagrangian, and I can then use the Lagrangian approach. We don't have to worry about the dissipation function and this f function, and we don't have to worry about these generalized forces because there are no forces acting on the system, right? So the only thing that we have to do is to compute the partial fraction of the Lagrangian over q1 dot, and that's simply m plus m times q1 dot. That's this term here. There's another contribution coming from here. It's quite simple. M q2 dot cos theta. The first term asks for the time derivative of the partial fraction of the Lagrangian. So it's the time derivative of what we've written above, and that's also very easy to write. It's q1 double dot plus m q2 double dot cosinus theta. It also involves the partial derivative of the Lagrangian with respect to q1, but there is no contribution in q1, so that's 0, right? So we have this term minus this term is equal to the generalized forces. There are no generalized forces, though. It's simply saying m plus m q1 dot double dot, sorry, plus mq double dot cos theta is equal to 0. So that yields my first equation using the Lagrangian approach. Okay, so now we have to do something similar with variable q2. Let's do that. Partial derivative of the Lagrangian with respect to q2 dot. Okay, this will give me m q2 double dot. Okay, it's this term here, and there will be a contribution coming from the last term. It's mq1 cos theta. Okay, here there's a mistake, of course. You saw, I guess you saw it. I'm taking the derivative with respect to q2 dot as a variable, so it's mq2 dot over here, right? So as before, I now need to take the time derivative of this partial fraction q2 dots. So that's very easy. mq2 double dot this time. mq1 double dot cos theta. And well, in here I forgot one term, right? So minus u plus mg q2 sine theta, because I was looking at my partial derivative of the Lagrangian with respect to Q2. And here there is indeed a contribution. It's mg sine theta. Okay, so I take this one minus this one is equal to the generalized force. There is no generalized force here, so we'll have the following equation. Okay, I'll skip the m's that are coming in from everywhere, so it's Q2 double dots plus yes, Q1 double dot cos theta minus j sine theta is equal to 0. Okay, and this is the second equation. Okay, I've removed the unnecessary stuff and I've rewritten my equation. Equation 1 is exactly the same, but equation 2 I've written q double dot, sorry, as a function of the rest. Okay, so what we are going to do is to take 2 and put it into 1, right? So we'll have mass, total mass, Q1 double dots is equal to, so it's not is equal, plus, and I'll take the first term, mj sine theta cos theta, okay, and then minus m q1 double dot, and it's a cosine square theta is equal to 0, right? Q1 over here, Q1 over here, so I have m plus m times 1 minus cosine over here, cosine squared theta times q1 double dot. You already see that this is now a sine squared theta is equal to minus mj sine theta cos theta, right? And so we obtain q1 double dot is minus mj sinus, I forgot the theta over here, sine theta cos theta over m plus m sine square theta. And without a surprise, this is of course what we obtained from the Newtonian approach, and we'll call this 3. And what we have to do is inject 3 into 2, okay, and we'll have q2 double dot is equal to, because we have j sine theta, we can put it up front, sine theta, we have something like 1 plus m cos square theta over m plus m sine square theta. So this is also the expression that we had obtained. We had to put it on the same denominator, and if you do that, you obtain q2 double dot is equal to mg sine theta over m plus m sine square theta. And again, without surprise, is exactly the same result that we had obtained previously, right? So previously I had done a check, right? Evolve linear momentum. Now I'm going to do another check. I like to do checks to see if everything is working fine. Let's have a look at what's happening if the mass of the wedge tends to infinity. Well, then you expect that the wedge is so heavy that it won't move, right? So you expect Q1 dot to be Q1 double dot to be 0, yeah, and for Q2 dot, well, you take just the gravity, but just the component that is vertical, and that will be J sine theta. Okay, so this is what you would expect from intuition, and let's see if that corresponds, right? Well, if big M goes to infinity, well, it appears in the denominator, and indeed you see that you will have here that Q1 double dot will tend to 0, yeah, and here you have masses appearing here and masses appearing here, so this fraction here will go to 1. So indeed, as M goes to infinity, then Q2 double dot will tend to J sine theta. Okay, another check, and it looks like what we have produced here is correct, and anyway it's exactly the same result as the Newtonian approach. Okay, let's take another example here, and we'll take a pendulum, but a pendulum with a spring, sorry. So there are actually 2 degrees of freedom. As with every pendulum, of course, there's the angle that the pendulum makes with the vertical axis, that will be called theta over here, and you have here the length. Okay, so these will be the 2 degrees of freedom, and of course we'll be using 2 generalized coordinates that are over here. Q1 will be theta and Q2 will be L, the length of the pendulum, and both are variables of time, right? So we have to keep that in mind when we have to take the time derivative. Okay, let's maybe start this time by the potential energy, with the potential energy. So this time it will be given by, well, there are 2 terms that are actually giving you potential energy. That's the energy stored in the spring. It has stiffness K, so we'll take it L minus L0 squared. Okay, so here L is the length and L0 is the length at rest. And there is this other term coming from gravitation, and it's mgy. Okay, and we'll see later on what it gives. The mass, let's say that the center of mass is there, RCM, I'll just write R is here, well, it's kind of easy, L sine theta, okay, minus L cos theta. Okay, so here I will have 1/2 K L minus L0 squared minus mj L cos theta. That will be my potential energy. To compute my kinetic energy, I will have to take the derivative of this one here to have the velocity vector, but don't forget that both quantities are time dependent, so I expect 2 terms in each element of the vector, right? So let's take the first one, I'm going to take first the derivative with respect to theta, so it's a cosine theta, theta dot, and then I will have the derivative with respect to time of L in there, so it's L dot sine theta. And we have something similar over here. The cosine gives a minus when you get the derivative, so it's a L sine theta, theta dot here, right? And minus L dot cosine theta. I need, for my kinetic energy, I need the magnitude of this velocity vector, which I will call v, which is what? Well, you have to take this one, theta dot plus L dot sine theta squared plus L sine theta, theta dot minus L dot cosine theta, and you have to square that. This will give me L squared cosine squared theta dot squared plus L dot squared sine squared theta plus double product, 2 times double product, 2L L dot. I have to make sure that I don't forget anything. Sine theta cos theta theta dot. I think I have got them all. Plus L squared sine squared theta theta dot squared plus L dot squared cosine theta squared, and then minus 2 times the dot product, so the double product, sorry. And here you have theta dots. Okay, this one and this one, they compensate each other. Okay, this one here and this one here I can group together, and I can group together this one here and this one here. So luckily things become a little bit easier. Yeah, see here that I forgot the cosine in the theta over here, right? So this one is, and the blue terms give you L squared theta dot squared, and the green terms give you L dot squared. So the kinetic energy is a half times m times v squared, right? What I've written here, nobody told me, but there's a mistake here. It's squared, so it's squared also. I need this one squared in my kinetic energy, so it's a half m L squared theta dot squared plus L dot squared, and this is your kinetic energy. Yeah. Okay, I've rewritten everything. I've added the Lagrangian, which is kinetic energy minus potential energy, and then I've written here the equation of Lagrange. Okay, I'll have two such equations, one from Q equals L, right, and another one from Q equals theta, because there are two generalized coordinates, right? So I will first write the partial derivative with respect to L dot, and that's m L dot. It's very simple, right? The only term that's giving contribution is this one times this one, right? And then now I have to, I'll need the time derivative of this thing. and that's very easy. That will be ml double dots. Now I can take the partial derivative with respect to L, and which are the terms that are giving a contribution. There is this one, so it will be m theta dot squared times L. This one will give you contribution mg cosine theta, and the potential energy from the spring will give you a contribution that is KL minus L0, right? So now we plug that into this equation. We have ML double dot, right, minus ML theta dot squared minus mg cos theta plus k L minus L0 is equal to 0, and I'll write that down a little bit differently. L double dot minus, you've seen I've divided by m, minus L theta dot squared minus j cosine theta plus k over m L minus L0 is equal to 0, and that will be my first equation. What I've done now for one generalized coordinate, I have to do for the second one. Q equals theta. So take the partial derivative with respect to theta dot, and as far as I can see, there is only one contribution coming from this term here, so I'll have m L squared theta dot. Now I need the time derivative of that, so the time derivative of the partial derivative of L with respect to theta dot. Two terms over here, so I'll have ml squared theta double dot plus 2, that's a 2, ml theta dot L dot, right? And now partial derivative of L with respect to theta, and as far as I can see, there is only one term. When you take the derivative of cosine, it's minus sine, so mg L sine theta, right? So now I plug it into this equation with q equals theta over here, so I'll have m L squared theta dot double dot plus 2 m L theta dot L dots plus m j L sine theta is equal to 0, right? Well, see that there's an m here, there's an L over here also, so I can remove the square, and I obtained my equation L theta double dots plus 2 times theta dot L dots plus j sine theta is equal to 0. So we have obtained a second equation over here, and this was my first equation. It is to be expected that you have two differential equations, as there are 2 degrees of freedom. Okay, well, I've rewritten the equation that we have obtained, and I've remove the rest. And as you should know by now, I'm a big fan of checking things. So suppose now we have a pendulum, okay, but without the spring. This is equivalent to saying that the stiffness here tends to infinity. Well, if you take equation 1 and you let k tend to infinity, the solution that you'll have is that L is equal to L0, and this means that L is constant, right? So if we take the second equation and we have L constant, this term here will be removed and we get what we expect, theta dot plus GL, 0 this time, sine theta is equal to 0. And this is indeed the equation of the pendulum that we have found much earlier in the course. Well, this concludes this series of videos on Newtonian and Lagrangian mechanics. I hope you found it interesting and that you liked it. Thank you.